Hello, good morning, everyone. How are you today? Do you hear me? And can you see the slides? Hi, Kingsley. Hi, Michael. Good morning, everyone. So today we will continue on the cold-formed steel structures, and our lecture today will be about understanding design of tension member and how to find the effective section or effective length of members subjected to compression or subjected to buckling. Okay, so let's start our lecture, and please stop me or ask me if you have any question. Okay, and a part of this lecture was quoted from lectures notes from Professor Johnny Mills. So let's start our lecture. So our lecture today will be introduction about the quick introduction about the cold formed steel, and then design of tension members uh, of cold formed steel structure, and then the element and behavior, buckling behavior of the elements. So these are mainly the topics we will be doing today, and the reminder will be explained or discussed in the next lecture or next week. So let's firstly, the cold formed steel structure, as you can see, is plate. We have a thin plate like this one, and this plate or this thin plate is converted into shaped or formed into shape using this machine or forming machine, okay, to give us this shape. For example, if you can see it, so this is our plate. So that's why the cold formed steel, as we mentioned last week, has thin thicknesses. It is, for example, maximized at 3.2. So this is the maximum thickness we can have, so that it is easy to be formed or easy to be bent like that. Okay. So give us this slide give us the key characteristics of cold formed steel structures or cold formed steel members. So shapes of cold formed are cold formed from flat sheets or flat plate, as we mentioned. The original mechanical properties of the steel are changed in certain areas of the shapes due to the cold forming. So due to the process of cold forming, the mechanical properties of the steel is changed a little bit. And this is the major difference compared to the hot rolled steel. Okay, we see now what is the difference in the stress strain curve for steel, for both types of steel, but the mechanical properties has changed or will be changed due to the cold forming process. Another advantage of cold formed steel that there is no standardized shaped, so you can form the cold formed steel for the shape you want. Thin material, in most cases less than or equal to around 3 millimeter. However, the standard allow up to 25 millimeter, but it is not available in the market. You need to uh, pre-order it so that they can form it for you. But it is hard and it needs special materials to bend 25 millimeter of steel. So the most or the common sections in the market are around 3.2 or 3 millimeter. The predominant or the most common failure mode of cold formed steel is local buckling, followed by post-buckling strength increase. So our problem in cold formed steel is the local buckling due to the thin walled nature of the section. Okay, so let's quickly have a look on this two diagrams here. So as you can see in these two diagrams, we have a comparison between the stress strain curve of steel. So this is the stress strain curve for the flat plate or flat sheet before cold forming to see what is the effect of cold forming on the cross section, on the mechanical probabilities or the cross section probabilities. As you can see here, we have the yielding point here, the ultimate point. So the steel from this point to this point is linear behavior, and then we have yielding. Then here at this point, the rupture or the maximum strength, and in this area we have the necking until the steel bar or the steel is cut somewhere here. Okay, so this is the original properties of steel or the typical properties of steel before cold forming. However, after cold forming, we need to shape the section or the sheet so that we need to make permanent deformation in the shape. Okay, so as you can see here in this area, this part is linear behavior or linear relationship. So in the linear relationship, we can't have permanent deformation. So to keep the permanent deformation, we need to skip this part so that we can have this deformation as permanent deformation. And that's why the shape of the stress strain curve for the cold formed steel is a little bit different. So if we start from here 0, so as you can see, we don't have we don't have a yielding point. So no yielding point in this part, as you can see, no yielding point. Okay, so the properties of the cold formed steel has been changed due to the fact that we need to have or we need to apply permanent deformation to the section so that we just have maybe a very short yielding part or almost no yielding sometimes. Okay, so this is the effect of the cold forming process on the properties of the steel due to the permanent deformation we apply to the sections. In this slide, we have some applications of the cold formed steel. As you can see, cold formed steel can be used in roof sheeting and wall sheeting and purlins or girts, sheeting, walling, and roofing. So these are usually or the most common uh, use of the cold formed section because these sections are lightweight sections, so it will help us to reduce the dead load or the own weight or the self weight of the structure element. So the application are roof and wall system, sheeting and supports, steel racks for supporting storage pallets according to standard 4084. Also, the cold formed steel can be used for structure members for trusses. Like in this, the trusses can be used hollow sections steel hollow sections like uh, square hollow sections, rectangular hollow sections, and circular hollow sections. So there's also some application of the uh, sorry, some application in the trusses, and also can be used in the frameless stressed skin buildings and domestic wall framing in some special case if the roof or the floor is. Hi Kingri, I will upload it to the website after the lecture, okay? Today. I just need to make some uh, updates to it, then I will upload. Okay guys, so we can use also the cold formed steel section for floor beams and joists in if the floor or lightweight floor, not for storage and this applications. Steel decking for composite construction. So this is another part. In some cases, they use the steel sheeting for composite slabs. So they have the sheeting. This sheeting work as permanent formwork for the slab, and then they add their normal slab with the normal reinforcement, and then apply the reinforced concrete in this part. So this is a type of composite slab where we can use the steel sheeting as well. Roller grain storage silos. In silos as well, we can use cold formed steel sheeting or cold formed steel sections. The advantages of the cold formed steel structure members are lightweight, this is the most important one, high strength, this is the second one. So the main thing in the cold formed steel that they have high strength to weight ratio. So they can carry or can support more loads compared to their weight. The third is ease of prefabrication and mass production. So if you have the milling or the forming machine, so you can easily produce or have mass production. Fast and easy erection and installation because of its lightweight, and also we can use like fabricated holes and so on. So it is easy to erect and install in the sites. More accurate in detailing because it is cold formed. Non-shrinkage and non-creeping compared to concrete. So it is much better than concrete in this part. Termite and rat proof. So compared to timber structure, so better than timber structure in this point. And uniform quality. So as you know, the timber structures has different or variable properties due to that the timber is a natural material, so we don't have like uniform quality. So the cold formed steel give us a uniform quality of the strength and other properties, so it is advantage for the cold formed steel. The capacity reduction factor in cold formed steel is a little bit different compared to the hot rolled steel. If you remember, what was the capacity reduction factor for all members of steel? Do you have any idea? Like the hot rolled one? Yeah, thanks, Kingsley. So point nine. So for all for structural steel members or hot rolled steel, phi equal to zero point 0.9. So 5.9 for design for tension member, compression member, flexion member, axial loaded member, right? And for flexion member, bearing and shear and moment. So all the members are phi equal to zero point 0.9. However, in cold formed steel, due to the different properties compared to the properties of structural steel. So sometimes for tension member, it's still the same, zero point 0.9. For compression member, due to local buckling issue is more critical here. So it is 0.85. For stiffener, it's ranging between 0.85 to zero point 0.9. For bending member, it is 0.9 to 0.95 because the cold formed steel post buckling behavior improve the strength in members like bending members. Web shear similar, zero point 0.9. Web crippling between 0.75 and zero point 0.8. This because again of local buckling or buckling behavior. The bolted connection and welded connection between 0.5, 55, 0.7, 0.5 to zero point 0.9. Okay, so up to here, this is the comparison to cold formed between cold formed steel and hot rolled steel. Okay, so they are different. So in the test, you need to memorize or go to the table to find the uh, the correct file. So here we are using in this part AS standard AS 4600. This for cold form steel. We will see later in the tension member. And here for structural steel member, as you know, what is the standard we are using in this part? AS 4100. So design of cold form steel is different or using different standard compared to structural steel or hot rolled steel. And here is the ultimate limit state for cold formed steel design, or this is the like expected failure modes for the cold formed steel member. So we have tension member yielding, so yielding in tension, overall column buckling, torsional and flexure column buckling, lateral beam buckling, distortional beam or column buckling, local buckling of relate element, shear buckling of webs, connection or connector failure. So based on the type of the member you are designing, you need to consider the applicable ultimate limit state, and they are a little bit or more than the ultimate limit state for structural steel because of the thin walled nature of the cold formed steel. Also, we have some serviceability limit state. So the serviceability limit state, excessive beam deflection. So I think we have this similar to the structural steel. Excessive story or overall building drift. Here excessive because if the member is thin, so it has I is small, so it will have high or big or large, make it large deformation or large deflection. So we expect large deformation or large deflections due to the thin nature of the members. Excessive also story or overall building drift. So if you have also building or story and all the columns are thin from conformed steel, So we expect that due to lateral load, the building or the story drift will be also high. Excessive post-buckling blade deformation, similar to the beam deflection. Transient vibration in the structure or vibration due to wind. Again, due to the thin wall. So for example, if you are designing a slab or sheet and we have live load on this sheet or whatever the load, so due to this thin sheet or thin plate, so the vibration will be too critical in this case, because if you have thin members, so the vibration will be more critical or more worrying to the people using this facility or this structure. So that is why vibration should be considered for the cold formed steel. Okay. Do you have any question, guys, for this introduction? Any question? No? Okay. So similar to before, the first member to design here and the tension member. So design according to AS 4600, the cold formed steel structures standard, and actually it is not only for Australia, so this is the correct name. So it is for Australia and New Zealand, so ASNZS for 600. So we have same standard like New Zealand. Okay, do you have this standard or have you accessed this standard or not yet? Should have a copy of this one as well. Okay, so let's start with the tension members. So the tension members can be found, for example, in members like this. What is this members are? Can you, any of you tell me what is this member can be? This member is bracing. So the bracing can be under tension or compression. So if we have a bracing member under tension member, so we have to design this member under cold formed steel structure, if it's cold formed steel structure. So here is the standard. I'll give this before this. So tension member, for the tension member under cold formed steel standard, this is designed according to section 3.2.1 in the Australian standard for 600. So the design capacity N asterisk should be less than or equal to phi t times nt. So it is similar to what we had before in structural steel or AS 4100. Okay, where phi nt in this case, or phi for the tension member, is zero point 0.9. So it is exactly the same as before, as hot rolled steel, where nt, if you remember, is the lesser of these two values. Is that correct? So we have two values, A gross F yield, this for yielding failure, and zero point 0.8 KT 0.8 KT AN F ultimate. This for rupture or fracture. Okay, where KT is given in table 3.2 in the Australian standard for 600. So similar to before, or similar to cold for hot rolled steel, we have two type of failure. One of them is yielding, one of them is fracture. So for fracture, we are considering the weak area of the member. For yielding, we consider the gross area of the member. So the capacity here in this case, area gross times F yield. So we assume that if this member under tension, so the area of the cross section will be subjected to yielding. If it is yielding, under yielding, so it is fail. So that's why we have A gross times F yield. For fracture, we assume that NT equal to a factor 0.85 KT point ANFU. In this case, this is our section, and because we may have holes or bolts in the section, for example, let's make it one hole only here. So if we have a bolt, so actually the weak area of this section is at the hole area. So we consider that this is our critical area. So if this critical area under tension force like this, so the fracture will happen at this weak point. So that's why we are using area net in this case. So here we use area gross, here we use area N. Okay, where Fy is the yield strength, Fu is the ultimate strength. So actually this is similar to hot rolled steel, so no new in this part. So what we need to do here in this calculation, we need to find area gross and we need to find area net, and usually area net equal to area gross only if we have welded connection. If we have bolted connections, we need to find area net equal to area gross minus area of the bolt holes, right? Then you can find area net and area gross. Then find area net. So area net using this formula here. So if we find the hole placement and the largest hole size, so we can find area net. Okay, so let's have a quick example on that. So if we have tension member or tension connection like this, so we need to find how much N asterisk can be applied to this connection, and we know the member details and F yield and Fy for the steel, and we need to find the design tensile capacity N asterisk. So to find N asterisk, we need to find N asterisk should be less than phi NT, where NT can be according to one of those, A gross times F yield and 0.85 times KT times AN times FU. Okay, so if we look to the solution here, so the first capacity is nominal capacity for the gross section area yielding. So this is the first one. So NT equal to area gross times F yield. Area gross is the plate width multiplied by the thickness. So the plate width is 100. The blade thickness is 2.5 millimeter. So this is area gross multiplied by F yield given as 450. So in this case, NT is 130. So this is the first one. Resistance factor is zero point 0.9. The second capacity is section fracture or net section fracture. So we have NT equal to 0.85 KT AN F ultimate. So we need area net. If we look to the example here, we have two balls in M12. So if the bolt M12, so the hole, how much do you know? Do you have any idea? No, not 15, King. Not 13 battle decks. So we can take it as if this our hole, so we should have tolerance. The tolerance of the whole bolt is 1 millimeter from each side, or 1 millimeter on the perimeter. So how much is the whole diameter? 14 millimeter. So if the bolt is 12, so the hole will be around 14 millimeter. So that's why area net will be 100 minus 2 hole. So if we look to the section, so we have one hole here, one hole here. So these two holes are 14 each. So how much the left part? So total is 100. So 100 minus 2 times 14 multiplied by the thickness 2.5, you get the gross section, the net area. Because from the table, uniform force distribution, because actually there is not much eccentricity between the applying the load of two plates, or if we don't know, we can go to the table here, table 3.2 to find it. So if we go to the table, we find that KT equal to 1. So the nominal capacity will be 0.85 times 1 times the net area times the ultimate capacity, and this give us a value of 173.4. So this means that NT equal to the minimum of 113 and 73.4. So it is 73.4. So this n mean n asterisk should be less than or equal to zero point 0.9 times 73.4. So it should be less than 66.1 kilonewton. So this is the maximum capacity we can apply to this members or this tension member, and it is controlled by or governed by the net section fracture. So this means the fracture will happen or will occur before the yielding. Okay, so this was for the tension member. This is similar to what we have done before in the hot rolled steel. And now we will look at the elements and behavior for members under compression. So as we know, the member under compression are susceptible to buckling behavior. So we are looking at the buckling behavior of the member under compression. So for the thin plates under compression or in compression, our main consideration is the local buckling consideration, or our main problem is local buckling due to what? Due to thin walled nature of it. Okay, so we have the theory for local buckling, two parts or two considerations, the elastic buckling and the post buckling behavior. So this is the theory for buckling, and then the factors that affect the buckling behavior is those ones. So these are the factors affects the buckling behavior. So what affects the buckling behavior of any plate? First part is the type of compression element. Second is the stress condition. So if you remember last week, we have cases of plate under uniform load or uniform stresses and gradient stresses, and the member also can be stiffened or partially stiffened or unstiffened. So in our calculation for buckling or for when we investigate the buckling behavior, we have to consider the type of compression element. Either they are stiffened or partially stiffened or unstiffened. We will see now the difference. And we should also consider the type of stress applied to the plate. Is it either uniform or gradient? So uniform means the stress if this our plate, so we can have same stress from both direction. So this is uniform, and we will find this in the flanges, mainly flanges. For gradient, if the plate we have, for example, two triangles like this, so the stress is not non-uniform or gradient. So this usually or mainly in the web, because the web is under bending moment, tension or compression. So part under tension and sorry, part will be under compression and part under tension if the moment is like that. Okay, so we should consider this cases when we are investigating the behavior of the plates. So the main concept or the major concept in the cold formed steel design is the effective design width or B effective. So if you remember last week, we have the concept of B effective or effective width of the member or of plate due to what? Due to local buckling. So due to local buckling, we have a concept of be effective. So in this part of the class, we will be looking at how to find the effective width, how we consider or how to find the effective width. So that our first parameter we should consider, or our first factor we should consider, is the type of compression member, or what is the edge condition for the compression member. It can be stiffened, partially stiffened, or unstiffened. What is stiffened means? Stiffened means the plate is, if we have something like this, if we have a member like this, so we have web, we have top flange, we have bottom flange, and we have these two parts are top lip and bottom lip. Okay, so when we are finding B effective, we should find B effective for each plate of the member. So this one also one note we should keep in mind, that we are not calculating B effective for one B effective for the whole member. We are calculating B effective for each member of the, for each plate of the member. Because as you can see, we have different type. We have top lip, bottom lip. We have also top flange, bottom flange, and we may have also web. Are all of them same condition as plates? What do you think? If they are under bending moment. So are all of them will have the same behavior under buckling or considering the buckling? Do you think that? No. So the buckling behavior for all of them will be different. So that's why we need to know be effective for each plate. And now which plates are stiffened, which plates are not stiffened in this member. So let's do it again here. So if we look to this member, so if we look to the top flange, so the top flange is stiffened. Stiffened mean it is supported at its two ends. So stiffened means supported at both ends. So what else is supported at both ends? If we look to the web as well, so this web is also stiffened. Okay, this flange again it is stiffened. So the bottom flange is stiffened. But we have only one condition for both flange. The lip should be strong enough to support, because this lip can be long, can be short. So based on some of the criteria given in the standard, we can consider it stiffened or strong enough to stiffen or not. But let's assume it is strong enough to stiffen, so all of these are stiffened plates. The only unstiffened plate is what? The lip itself. So the two lips are unstiffened because they are supported at one end and free on the other end. So if we consider this our lip, so the lip is free at this end, right? And actually it is supported on the other end. Okay, so this is the difference between stiffened and unstiffened. And partially stiffened means, so for example, if we have something like this, partially stiffened, for example, if we have this flange and this flange. So when we can consider this flange is partially stiffened, who can give me idea about that? Do you know? What is the difference between partially stiffened and this case? So in this case, what we have here for this plate, we have one support here is the lip, and we have one support here is the whip. But the idea is here in this case, this two lips, we have two lips, but the two lips are not strong enough or short. So they are there, but not conforming the criteria of the of the support or the stiffener. So they are not strong enough to support the flange. So they are short lips. So in this case, we can consider it as partially stiffened flange. So the top flange and bottom flange in this case are partially stiffened. The web still stiffened, no problem with the web. So this is the difference between partially and stiffened and unstiffened plate. So let's have a look here quickly for the types of member. So if we look here, this our top flanges are stiffened, the web are stiffened. Here for the flange, stiffened flange, stiffened flange, stiffened web, stiffened web, stiffened web, stiffened bottom flange, stiffened web. So all these are in red are stiffened blade, right? The only thing here is this and this lips, this flange are unstiffened. Here, if we look to this types of sections, so we have flanges are stiffened or unstiffened, unstiffened. They are only supported at one end. Here as well, unstiffened. Here as well are unstiffened. So all the green are unstiffened. And here the web is still stiffened. Okay, so all the greens are representing plates that are unstiffened. All the reds are stiffened plates. Okay, do you have any question, guys? No question? Do you want to rest now or continue? What do you think, guys? Are you still here? You want rest? Nobody is here. Can you hear me? Okay, Michael, thank you. So 10-minute break, and we'll see you again at 10:14. Okay? Thank you. Thanks, Michael, for responding to me. Everyone is sleeping or what? Okay, so we have 10 minutes of break and meet again. See you at 10:14. Thank you, guys. Let's see you in 10 minutes. Okay, guys, can we continue now? So we have talked about the difference between stiffened and unstiffened plates, and we have in between case which is partially stiffened if the lip or if the support is not enough to stiffen the plate. Do you have any question about this part? No? Okay. So let's see how the stiffened plate and unstiffened plate behave according to section 2.2 of the Australian Standard 40 for 600. So I will show you the section on the standard. So here is the section we are talking about. Effective width of stiffened elements, and all the information are extracted from here. So as you know from last week, the formulas for cold form steel is a little bit complicated compared to hot rolled because of the thin walled nature. So this is section 2.2, and I hope you have a copy of the standard with you ready so that you can have a look on the formulas and so on. Okay, so let's go back to our slides. For stiffened plate element, as you can see, if we have a beam or a column, the beam under bending moment, M and M, this will be the behavior of the beam. And as you can see, due to, let's let's talk about this one. So if this our moment, so this is our neutral axis. So the top flange is our compression flange. And due to the stiffened support on both ends, as you can see, these points cannot move up or down. So these points are at a place. The point that move up and down is the middle point. So if you can see this line here in this direction or this line here in this direction. So actually these points in the middle are free to move or buckle up and down. So actually the stiffen plate will not buckle at the ends and it will buckle only in the middle. Similarly for this column here under axial load N and the N. So if we look to any plate of this plate, let's talk about the side plate here. So as you can see, this is stiffened edges. So these edges cannot move and only these points here can move. So this point, so these points can move or buckle because they are free to move uh, right and left in this case, here up and down in this case. So this is how the buckling will look like for stiffened member. For unstiffened plate or unstiffened member, section 2.3. So if we have beam again and column, for beam, if we have, this is our neutral x, so our compression flange is the top flange. So the top flange is supported at one edge, free on the other edge. So that's why, as you can see, on the free edge, these points can move up and down freely. So almost all the blade is subjected to buckling because no thing to prevent the movement up and down. Similarly, for this column, if we have in, in, so for the column, these edges are stiffened, but the other edge or this edge here and this edge here are free to move. So these points, all the free edge points, are buckling left and right. So you can see how much the difference between the two cases for stiffened and unstiffened plate. So in the buckling behavior or in the calculations, we need to consider the effective width of is different for unstiffened and unstiffened plate. For stiffened and unstiffened plate. Let's have a look on this example here. So for this example, we have a plate, stiffened plate. Okay, for this stiffened plate, so we are looking at a stiffened plate in this case. So this stiffened plate is under uniform stress. So this one case we may have plate under uniform stress. And the two edges or the two other edges of the plate are stiffened or simply supported as you can see. So these two are simply supported. So under the stress, these points will be able to move up and down so that they are under buckling. So these points are under buckling. So what is the stress or the critical stress for buckling for this case? If CR, the critical stress equal to K, the buckling coefficient multiplied by pi squared E divided by 12 1 minus nu squared and multiplied by W or T over W all squared. So I will remove this one. So this is our formula for buckling stress or for the critical buckling stress. And this can be found here as well, show you on the standard. So this close here. So this is the elastic buckling or plate elastic buckling stress. Close to 0.2, 0.1, 0.25. So if we go back to our slide, so this is the formula. What is the formula means, or what is the formula parameter? So let's write it down here. So the critical buckling stress, which is the critical stress when the buckling starts. So this is the critical buckling stress. So after this stress, the plate will buckle. Before this stress, the plate will not buckle. Equal to K, the buckling coefficient, based or according to the plate is stiffened or unstiffened, and also depend on the type of stress. So all these are parameters applied. So it is uniform or non-uniform, uniform or gradient. Multiplied by squared E divided by 12 minus 12 multiplied by 1 minus nu squared. All of this multiplied by T over B or W squared. So all this part is constant for the material. What is E? E is Young's modulus of steel. How much is Young's modulus of steel? Do you know? 200,000 MPa or 200 gigapascal. What is nu? Nu is Poisson ratio of steel, which is 0.3. So this means this number is a constant. If each of them is constant, so this number in total is a constant. Okay, so all this part of the formula is a standard. Sorry, constant. So actually, the buckling, critical buckling stress, FCR, depend on K and the plate dimension. T, what is T? The plate thickness. What is B or W? The plate width. So if we go back to our slide here, so in case of uniform stress, this is our formula. So what we need to know to understand the critical buckling stress, we need to know K. So K, if you remember from our last week discussion, we have different value of K, and this table is important for you and for our course, so that you need to keep in mind the value of K because we are frequently using it in our cold formed steel design, and they are mentioned in the standard, but sometimes it is hard to find them in the standard because they are not all in the same area or not in the same section of the standard. So if we look here quickly to the standard under the same section, so here in this clause, if you can see, the buckling, the K is blade buckling coefficient. K is equal to 4 for stiffened element supported by a web on each longitudinal edge. K values for different type of element are given in the applicable clauses. So it is not actually given in one clause or one part of the standard, so you need to keep in mind where or what is the values we usually use in our calculation. So in this table, we summarize K for you. So actually we have four four cases for K. Case one, if we have plate stiffened under compression, how much is K? 0.4. So it is 4, sorry. So if the plate is stiffened in both edges and under uniform stress, as you can see, How much is K? 4. So usually this is for stiffened flange. 2, number 2 is if we have only one edge supported and other edge is free. So this where this will be in unstiffened plate or unstiffened flange. Usually in unstiffened flange. So in this case, how much is K? 0.425 or approximately 0.43. So this means that K for stiffened almost 10 times K of unstiffened. Third case we may have in our calculation is plate simply supported in both edges and under shear. So in shear we have shear here. So in shear, how much is the factor? Point 5.34. So this is the factor for stiffened under shear. The third one, or sorry, the fourth one is blade also stiffened from both edges, but under gradient stress. This usually what? The web. Web in bending moment. So in this case, under bending moment, the factor is 23.9. Why the factor here is large? Because of the post buckling behavior of the plates in bending. So the plates under bending, they gain more strength after buckling due to the post buckling behavior. Okay, so this table is important for our calculation. And now for the post-buckling stress distribution, this a reminder of what we have or what the theory for last week. If you have this stiffened plate here, so the stiffened plate actually, if the stress less than, and this under moment, so this is the stress in this case. If it is less than the critical, if F1 less than the critical, so the stress is uniform on the plate. So this means you can use the total weights of the member. But the problem is when the stress exceed critical yield, or sorry, critical elastic buckling. If F2, this is the stress in the plate, exceeds the critical buckling, what happened to the stress? The stress in the midspan will be less than on the edge because the edges are stiffened. So no buckling will happen here, but here it will be reduced due to buckling. Okay, and this will keep changing until the plate reach yielding. So at yielding, the stiffened point will be will have higher stress F3 equal to F yield, and the midpoint here will have less stress due to buckling. Okay, so actually that's why we can't use B or W of the member. What we should use? We should use B effective or the effective width. So this is just a reminder what or why we need the effective width. So the idea behind this method is to, instead of using the non-uniform stress, as you can see, we just use uniform stress in this part and uniform stress in this part, and we ignore the middle part. Okay, so this part ignored. So this means that instead of using the whole W, we use be effective over 2 from left, be effective of 2 from right. So this can be interpreted here, or I can draw another diagram quickly here. So the actual stress on the plate will be something like this due to buckling. So we have here lower stress compared to here. So here F3 equal to F yield. So this is the type or the shape of the stress we have. So this is our total plate width. So instead of working with the non-uniform stress, what we have done is just using approximately. We remove the part that under buckling and ignoring this part here and convert the stress to equivalent stress here. So actually this is converted to this. So this means this part is not effective with us, and this F3 equal to F yield, F3 equal to F yield, and instead of B we have B effective. And we will see now how much is B effective compared to B. B effective equal to rho times B, where rho is a factor less than or equal to 1. So this is the effective width concept. Just to simplify or get equivalent section compared to the actual section due to why we have this concept again due to local buckling of the member. So now let's have a look on the formulas from the standard. So the effective width expression can be found in section 2.2, equation 2.2.1.23 and 4, okay, for the following cases. So B effective equal to B if the buckling coefficient lambda or the slenderness ratio lambda less than 0.673, and B effective equal to rho B when lambda is more than 0.673. This means in this case rho equal to 1. No, rho is 1 if the slenderness ratio less than 0.63. Okay, actually this should be 1. Anyway, let's have a look on the standard quickly. Here is the two formulas from the standard. Can you see them? So if lambda more than 0.637, B equal to B. If more than 0.6673, it is B effective equal to rho B. Okay. Where? So this is 2.2.1 and 2.2.122. Where? Sorry, I just missed this one. So what I have written just is the number of the formulas here, where we should know now how much is rho and how much is lambda. So rho is equal to this formula here. So rho equal to 1 minus 0.22 divided by lambda, all divided by lambda. And lambda is equal to 1.052 divided by root k, multiplied by B over T root F asterisk divided by E. These two formulas again in the standard here. Okay, and as you know, rho should be less than or equal to 1 because it is a reduction factor. Okay, so the formula we have written for lambda coming from this formula here. So it is actually lambda equal to root F asterisk divided by F critical, where F asterisk is the design stress in the compression element. We will see now. And F critical is the value we studied earlier in this lecture. So what we have done is just substituting F critical with its value here, and we finally got this formula. So this formula for lambda here is actually derived from the original formula, which is lambda equal to root F asterisk divided by FCR. And we replaced FCR, which is equal to K times pi squared E divided by 12, 1 minus nu squared multiplied by T over B whole squared. So this is how to find the critical width of the member. And here is a relation between rho on the vertical axis and lambda on the horizontal axis. So as you can see, when lambda increase or the slenderness ratio increases, what happened to rho? Rho decrease. So the relation between lambda and rho is inversely related. So lambda inversely related with rho, or rho inversely related to lambda. So rho equal to or inversely related with, and actually the relation is quadratic. So that's why you can see a quadratic curve. Okay, what this mean? This means that when lambda increase, rho decrease, and this means effective width decrease. So increasing lambda will reduce our effective strength width, which means in reducing our strength. Okay, and here some examples of the effect of local buckling in bending stiffness. Because what we will do after we got from here, be effective from here, what we can do with be effective? Do you know what we will do with be effective? So be effective equal to rho B. So rho is a reduction factor, and it can be less than or equal to 1. So using beta effective, we will find A effective area of the section. And what else? We can find I effective or Z effective, which are effective section stiffness or flexure stiffness or effective section inertia. Have you seen Z effective before, guys? Have you seen Z effective before in hot rolled steel? In hot rolled steel, we also need to find Z effective, which is the effective section based on the section compact or non-compact or cylinder. So if we look to this example here quickly, if we have a member like this C-section under bending moments, so our top flange will be our compression flange, right? So as you can see, due to the buckling, this part in the middle here will not be effective. And when we increase the stress, this part become more ineffective. So what happened? We need to find the effective width, which is be effective over 2 here and here. So this mainly in the areas when we have large moments. So in this part we have large moments. So this part we will have be effective width less than B. Okay, so that's why the inertia here in this part, the red part, is I effective less than the original I. However, on the areas, on the edges, here and here, due to the moment is too low in this part, so we don't have reduction of the width. That's why this area we have the same I, no reduction in I for this part. Okay, so this is an example of the effective inertia or effective stiffness due to the applied moment. And here as well, effect of local buckling on a column section. So if you have a column section under normal stresses from up and down, so this is how the effective length, effective width affect our calculation. So this part here and this part here of the column will be under local buckling. So this part should be excluded from the section. That's why we have be effective over 2 here, be effective over 2 here. We have be effective 1 over 2 here, be effective 1 over 2 here. So all this part, the pink part is excluded from the section and only the light blue one will be with us. So this make our new section like that. So this is our effective section. So as you can see, the effective section is smaller compared to the original section or the section we are studying. Some important definitions here, we may have a look on them. Okay, some important definitions are B is the flat width. So flat width means we ignoring the radius of bend here. So this is B, effective flat width. And for a web, it is also, as you can see the notes here. So for the web, also it's starting from after ignoring the radiuses or radii. So this is B web here as well. So we are only looking at flat dimension for web and for flange. Okay, for lip as well, D is the flat dimension of the edge stiffener. So D is the flat dimension of the lip. Okay, so we have, this is our dimension to use in our calculation. And here is the maximum slenderness ratio according to section 2.1.3.1. So this section give us the maximum slenderness ratio. Just have a look on it. So section 2.1.3.1. So this is the maximum flat width to thickness ratio for use with the effective width method. So we need to refer back to these values here. For a stiffened compression element, we have 60 for a simple lip. For any other kind of stiffener, we have 60 or 90 based on the inertia IS and IA. If I is less than IA 60, if I is more than IA 90. For a stiffened compression element with both longitudinal edge connected to other stiffened element, 500. For unstiffened compression member, it is 60. So this is our limits for the slenderness ratio. If we go back here. So here section stiffened compression element with each stiffener, like the flange. So B over T should be less than or equal to 60. So if this T and this B, so B over T should be less than or equal to 60. For member stiffened compression element, here in this case, B over T should be less than or equal to 500. So in this case, the difference that this flanges here are connected to webs from both ends. So in this case, if it is connected to webs from both ends, so it will be stronger, so that it can be less than 500. Here in this case, it is connected to one edge here to lip. So in this case, the support on one side is not strong enough, so 60. In this case, 500. The third one here, for unstable compression element as well, B over T less than 60. So similar to the first one, B over T should be less than 60. So here, unstiffened flange, and if you're calculating for the lip itself. So B over T should be less than or equal to 60. This for web, unreinforced web, D over T should be less than 200. For reinforced web, satisfying section 2.71. If we have bearing stiffeners less than 260. If we have bearing and horizontal bearing and intermediate stiffener less than 300. So all this limit should be considered when we designing the or finding the maximum stress section slenderness ratio for the blades for our calculation. And here is the value of K for uniformly compressed stiffened elements. If we have a uniformly compression stiffened element like top flange in a member under moment, if we have a top flange of a member under moment, so the top flange will be under uniform compression. Okay, so the effective section for our flange will be this part in red. Okay, this part is B effective over 2, B effective over 2. So we have B effective equal to rho times B. Then you need to find rho equal to 1 minus, rho is here, minus 0.22 divided by lambda and divided by lambda. And then you find lambda equal to 1.052 divided by root k multiplied by b over t multiplied by root f asterisk divided by e, where f asterisk is the applied compression stress on the flange. Okay, k, the buckling factor here, the buckling coefficient here will be taken as 2. Sorry, 4. Why the buckling coefficient will be taken as 4? Because it is stiffened plate under uniform compression. Okay, so this one common case we have, and now let's have a look on an example to find the effective section width or effective thickness, effective width of the member. So if we have this member here, beam section under moment, so we have moment. So which one is compression flange? The top flange is our compression flange. So flange, this is our compression flange, and the whip is under what? Or the two whips under gradient stress. So we have part under tension, part under compression, because the top part will be under compression and the bottom will be under tension. Okay, let's have a look on this example. So the yield strength for this member is 300, thickness is 2.5, R is 2.2 T, R is the radius, will do 2 times the thickness, which is 5 millimeter. So R is the radius here. So this R equal to 5 millimeter. Usually it is 5. Here it is given as 2T. So we need to find the effective width of the compression flange for strength. Okay, so first of all, we need to find, our first step will be to find B. How much B in this case? B will be 100, the total width which is given to us, minus 2 times R plus T. So here we have two parts here. So we have What is this? So we have t from left, t from right, then we have 2r. So b, total b minus 2r plus t. Okay, so in this case, b will be 885 millimeter because this 5 is r is 5, t is 2.5. So b over t, the slenderness check, b over t equal to 85 divided by 2.5 equal to 34. We check or compare to 500. Why we compare to 500 here? If we go to this case here, we have stiffened compression element and connected to two webs. So it is 500, okay. So no problem with the the dimension. Then we need to find what? Lambda. Why we need lambda? Because we need rho. Rho equal to 1 minus 0.22 divided by lambda, all divided by lambda. So we need our first step to find lambda. Lambda is equal to what? 1.52 divided by root k multiplied by t over b over t multiplied by f over e. So we know k. What is k in this case? K is 4. So we need to find lambda. K is 4. Why k is 4? Because stiffened plate under uniform stress. Okay. So we have k is 4. B is 85. T is 2.5. F asterisk is yield strength equal to 300 MPa. E 2 times 10 to the power 5. So lambda for this plate is equal to 0.693. So lambda is 0.693 more than 0.673. So it is B effective equal to rho times B. So we need rho. So rho equal to this part here, 0.22 over lambda and divided by lambda. So this replaced with 0.693. This replaced with 0.693. So give us rho equal to 0.985. 0.985. This is our rho. So B effective equal to rho, which is 0.985 times 85, give us 83.7 millimeter. Okay, so is this okay? So this was our first requirement to find B effective. So to find B effective for the flange or for any blade, we need to find the dimension B and T, then check the dimension, then find lambda to check if we need rho or not. So we find lambda, then find rho, then find B effective. Okay, do you have any question, guys, for this part up to now? All good? No question? Okay, thank you. So we will end the lecture up to here, and I will see you in the class in few minutes. Thank you. See ya.